I'm going to talk about visualization, and in particular, this is a big topic. There's lots of different ways we might visualize our data, and so I'm going to start by talking about the slice plot class. And this notebook is up online on that GitHub that Madikin, I believe, shared the link with either in the chat or on the Slack. And if I make any updates to it, I'll update it there as well. And we'll be sure to send that out more as the workshop continues. We'll send reminders to where that is. Part of the reason for starting with slice plots is that a slice is sort of the easiest way you can imagine taking some three-dimensional data set and making what has to be a two-dimensional image, because that's what our screens or the papers that we publish are going to show. And so the slice is as the name implies, simply taking a slice through the whole data, intersecting your data volume with some plane, and visualizing the data values that plane intersects. So I'm going to use the same data set that we've used before. I'm not a cosmologist, so some of these fields have no meaning to me, but this is a reasonable sized data set that, it won't slow down this presentation because it's too big to visualize. But you can certainly go back through this notebook and rerun it with some other data set, hopefully one of your own, just to get a feel for how these different operations work. So just to sort of tie some things together from the morning, the way I think of yT is the primary design of yT is to enable you to visualize volumetric data. So this is where you have some physical location in a volume that can be indexed perhaps by an XYZ. There might be some complexity in that with a AMR hierarchy or an unstructured mesh or something like that. But yT inside knows how to find a value for a given point XYZ. And so at every point XYZ, you have one or more associated data values. And somehow you want to make an image from that. So the different plot types that yT does includes slices, which we'll talk about today, projections, which Madikin sort of alluded to some in the previous tutorial, and that'll be a focus tomorrow. Simple plotting a line through there, or profiles. Matt showed this neat animation, which I have no idea how he made, where he had this cool curved path and it was updating the data values as it went through there. Phase plots, which Stephanie will talk about tomorrow, and volume rendering as well. And stuff that we won't talk about surfaces, but I imagine that's something we could talk about in the free time. One of the things that I always do when I need to make some sort of plot or I need to do some sort of analysis with yT is I start with the cookbook. And the cookbook is a section of the docs. Let's see if that comes up. It does. That basically has simple recipes, the code and the output following it, for how to do different visualizations or different analysis in yT. And for me, 90% of what I need to do can be answered just by scrolling through here, finding an image that kind of looks like what I want, and then using that to adapting that recipe to my own needs. And so a lot of what I will show today has some lineage in the past to the cookbook. The other thing that I would mention is that hopefully at some point, some of you will want to contribute back to yT itself. And if there's a type of visualization that you do or analysis that you do that isn't represented in the cookbook, adding your own recipes back to the docs is a great way to get started contributing to the yT community. And that's something we'll talk more about on on Wednesday, sort of the community infrastructure. But that's the way I got started with yT, is trying to add some examples that to me were not as cosmological, and applied to the way I think of data. So always start at the cookbook is sort of my advice. Oops, and I have no idea what I just did. Problem of having too many windows open. Oh, I think I separate that out. Okay. So Madikin already showed us the field list, and so I won't go over it in all this detail, except I will admit that the difference between density with a capital D and density with a lowercase d is something that has confounded me. In the front ends that I work with, they're the same, but for Enzo data, they're different. So I'll switch somewhere midstream in this notebook, and that's just because I forgot to capitalize things at some point. So just to get started, Madikin did a wonderful overview of how to do different types of reductions on data, and one of which was a cut through the data, and then she showed how to plot that. The slice plot method itself, it's actually a class in yT, provides a nice high-level overview, a high-level interface, excuse me, to doing what she had done in that notebook before. And at its simplest, it just looks something like this. yt.sliceplot, give it the data set. That's the data set that I read in at the top, the isolated galaxy data set. And give it the orthogonal direction. That is, I want to make a slice that's perpendicular to z, so it's going to be the xy plane, and give it a field. And when I do that, for this isolated galaxy, which I'm not a galaxy person, this doesn't look like a galaxy to me, but I'll go with the title of the data set, I have a slice through the data. And by default, this is going to slice through the middle of the domain, and by my selection, it's going to slice in the z direction. I could slice in x, and so then if I slice in x, I see that my axes now are z and y. It looks largely the same. So this is something that's somewhat of a spherical galaxy. Few things to note here. This example is something that's called an axis-aligned slice plot. What that means is that I am using one of the 3 coordinate axes as my normal to the slice plane. That's actually rather natural. If you think about the simplest way to represent volumetric data, just a cube of data, there's, in terms of how the computer thinks about it, there's a natural way to slice an array and do that operation. So this is actually probably the simplest way you can do a slice, but it doesn't have to be that way. And I don't think I'll talk about it today, but I'll talk about it tomorrow. You can define the slice to be off axis with the normal as some arbitrary vector. Another thing to notice, and this is something that causes me great confusion, and so I take a little bit of time to dwell on it. The coordinates here are rescaled such that 0, 0 is at the center. So the whole coordinate system has been shifted such that the center of the plot window is the origin of coordinates. I don't know why. I think that's just a historic artifact in yT, but we're going to quickly undo it below because I think it's more natural to have the coordinate axes conform to what the coordinates were in the actual data set. Another thing to note, the units have propagated through and they appear on the plot, megaparsecs. And this is in terms of the code units because as we learned, myself included earlier, this capital D is the field on disk, and it's stored in terms of code mass over code length cubed. If I change this to lowercase density, it uses the alias. I don't know what the exact term was that Matt used for this morning, but now I have the more familiar grams per cubic centimeter. These are tiny values for me, but I'm told those are absolutely fine for a galaxy. I mean, that's like round off for me. Okay, so let's make the plot a second time. And the other thing that also is perhaps unintuitive is that by default the log of the density is plotted. For most of the plot variables, a log is automatically applied. So as I mentioned, the shifting of the axes can be a source of confusion, and we can undo that. And we can undo that by passing in a keyword pair. So the keyword argument is origin to specify how you want the origin of coordinates to be defined. And we're going to set it to native. And what that means is use the natural coordinates that the data was had in the simulation. I'm also going to capture the output of yt.sliceplot into an object, a variable just called sp. And if I don't do this other sp here, it just does its thing but doesn't show the plot. And so if I want to show it, I guess you could do sp.show, but in Jupyter, if you just put the object itself on its own line, it'll show the plot. And now if I see this plot, now my axes have been scaled or unscaled, I guess, so that they agree with what the natural was on the disk. And so now the origin of the coordinates is lower left. That's what it was if you read in if you look at the actual information that was output when the file was read. Okay, so I captured the output of sliceplot into a variable, and I can look at what type that is. And if I do just the Python type command, I see that it is an axis-aligned slice plot. That's what we had talked about before. Axis-aligned is the special case where the orthogonal direction is one of the coordinate axes. It's part of the plot window module in visualization in YT. And if you actually have your YT source somewhere and you navigate to YT/visualization/plot window, you can look at the gory details of how this is implemented. I usually do help and then the option, but it seems all the cool kids this morning were doing using the question mark, which is, I think, just a Jupyter specific thing. And as with all the other YT features, there's extensive help provided by the doc string that the function provides that tells you all the sort of things that you can set in here, and we'll go over some of those very soon. You can save the image. So operating on the slice plot object that I stored, I can use the save method and save it to disk. And if I do ls, I see it's there, and this is the current time. This is an image magic command. If you have image magic installed, I usually like to just look at things, and it shows that it's 1302 by 1104 pixels. It's a strange number of pixels, and that's because by default, I think it removes any excess padding. And I was gonna, let's see, this is where we try to do things live. If we actually look at the slice, you can see this is what the slice plot looks like. It looks like it looked like on my in my Jupyter screen. It might have squashed it a little on here. All right. Let me find where I am in Jupyter. Okay. So usually after you make your first plot, the next thing I want to do is I want to change the colors just because I want it to look pretty. I'm going to remake my plot. Oh, I'm not going to remake my plot. I'm still working off that same slice plot object. And the first thing I'm going to do actually is I'm going to change the data range. So if I look up here, it plotted the full range of density as it appeared on the disk, something a little bit less than 1 in code units up to a bit more than 1 million in code units. And I can change the data range by using the set zlim method. And I give it the field density, I give it the minimum value, I give it the maximum value. And when I do that, it's going to spit out a new plot. And now you see the color scale ranges only from 10 to 10,000. So I've clipped the range, and anything that's more than 10,000 in density in code units is just clipped to yellow, and anything that's less than 10 is this, I don't know what color you'd call that, but whatever color that is. And so restricting the data range is something that you probably want to do pretty often if you want to just look at specific parts of the field. And then finally, you can set the color map. Magma is one that I like a lot. It kind of looks kind of fun. You could pass in any matplotlib color map. yT has its own color maps. The default, I don't even know how to pronounce that, Arbre or so, is the default color map. If you go to the yT color map page, it'll show you examples of all the different color maps you can choose from. Some of these are better than others. There was a lot of effort in the last few years to make color maps that work well for all different types of color blindness and reproducing black and white and so forth. And the default's a great choice, but there's other ones that also work quite well. All right, I'm assuming that someone's keeping tabs on the hand raising, and I'm just going to plow forward until I'm interrupted.
I have seen no hands raised.
Okay, thank you. This is my first acknowledgement as well that people actually hear me, so that's always good. It's a very surreal experience doing this virtual.
Yeah,
all right.
I can't stand talking to my own screen.
It's weird, yeah.
Also, Medican has her hand raised now.
Yes.
Okay, do you have a favorite color map other than Magma? Anything like fun you like to use?
It depends. So I look at vorticity a lot.
Mm-hmm.
And or entropy, magnitude of vorticity. And so I like the symmetric ones, like the BWR. I think that works well for that. I don't know. I tend to like the reds, I think. So I think that's why I like the Magma over the default one.
Okay, cool.
Just play with them. Certain ones, like if you're plotting something symmetric, like velocities can be positive or negative, I like for a neutral color to be in the center. I think it helps your eyes more. That's the way I normally think about it. Okay, but this one I think looks cool. It looks like magma. It looks like a volcano here, I think. All right, so now let's zoom. Again, we're going to work off of the object returned by slice plot, the slice plot or axis aligned slice plot object. And we can just, this is just making the same plot I've made before. I'm going to stick with the origin equals native because that's how my brain works. And after I make it, I can zoom. And so I just use the zoom method. So sp.zoom and give it a zoom factor. And now I've zoomed in by a factor of 2. And something that I think I knew, but I always forget and then relearn, is that if I call zoom a subsequent time, it zooms off of the previous zoom. Let's see. So, I just reran that. So now this zooms a factor of 4 from what that previous factor of 2 was. And this zooms a factor of 5 further still. And so you can really start to see the structure. You can also start to see where the coarse data is and where the finer data is, because it's nicely preserved in the way that it's plotted, that you actually see in how I think about it, sort of the finite volume nature of the underlying data in this case. I'm going to regenerate it again. So I'm going to be resetting the plot a lot of times as I do these things. And I'm always, actually, this is where I discovered I wasn't always doing the same thing. I thought I was always doing the same thing, but now I slipped in the lowercase density here. And the scale is more physical, but these are really small numbers to my mind. But here's our same slice plot as we had when I started out earlier. And now, instead of just calling zoom, whoops, that was me executing that. Instead of calling zoom by some arbitrary factor, I'm going to set the scale, the size of the box that I want. So this overall box is a megaparsec. And I'm going to say that I want to set the center of my box to be 400 kiloparsecs along X, 400 kiloparsecs along Y. Notice that when I use set center on the slice plot object itself, I only need to specify 2 coordinates. And those are the 2 coordinates in the plane. Because I've already chosen the coordinate in Z in this case that my slice plane intersects. And so now I'm choosing just the coordinate in the plane to actually set my center in the plane. And I'm going to set the width to be 200 kiloparsecs. So this is going to be something right around here. And it's going to go from like here to here. It's going to give me a little zoom in of this region. And both of these are methods that operate on that axis aligned slice plot object. So I'm building off of that previous plot that I made. I'm doing sp.setCenter, giving it the coordinates in plane of my center, sp.setWidth, giving it the physical width that I want. I brought in that kiloparsec unit from the YT unit system to let me do that. And this is what I see. And it looks like we said it should look. If we looked above the center of the galaxy, or again, I'm not a galaxy person, whatever that is just there in the corner, as it should be if I started out 100 kiloparsecs off the origin in each direction and have a 200 kiloparsec box, then this is going to be the upper right corner for my plot. And so I can see that I've done that. And this is a more controlled way, perhaps, to zoom, where you actually set exactly what it is you want in terms of the center and the width. And a lot of operations in YT work in terms of passing in a center and a width. I think I said this already. When we use set center, we only specify the coordinate values in the slice plane. Alternately, if I do it when I generate the slice plot itself, I can specify the center now as a tuple with 3 values. And since this is a slice orthogonal to Z, the first 2 values are the center in the plane. And the last value is the Z coordinate that my slice plane is actually going to cut through. So by default, it was going through the center of my data set. Now this allows me to specify exactly which point, including in that orthogonal direction, my slice plane is going to cut through. And again, I can specify a width. And when I do this, it looks very different. The color scale, the data range is much smaller because now I'm off. I'm 100 kiloparsecs away from the center in the orthogonal direction. And so I'm really only seeing the outer parts of the galaxy where the density is much smaller, or so I learned in galaxy class. So that's pretty cool. And so that gives you pretty fine control over exactly how you want to do your slices. And of course, I've been using Z because I've been lazy and because my last name starts with a Z. But you could do X, Y, or Z here to do your slices in any of the 3 orthogonal directions. Tomorrow we'll talk about the off-axis slices. So there's many ways to set the center of the domain. If you get help, ask for help using either the question mark or help slice plot and look at the center, you'll see a lot of these. In addition to just specifying an actual tuple with the values, you can specify the just center or the letter C for the domain center, max or M for the maximum of density, min for the, and then a field. So I can make my slice plot of whatever field I'm looking at go through the minimum or maximum of some other field. And so these are useful things that you might want to do if you're looking for the behavior of your simulation around extrema, for instance. And so I left this as an afternoon exercise to play around with this setting of the center, setting of the center that the slice plane plots through, to instead try to do it based on some physical data feature, like where the temperature is the highest. All right, so so that's the basic overview of slice plot. We're going to do two more things today. We're going to look at how to visualize multiple fields. So slice plot can actually take a list of fields or a tuple of fields and do the operations on all of them. But there's a little bit of work that needs to be done if you want to group them together in a nice array of figures or axes, if you use the matplotlib lingo, to make a sort of publication quality plot. And the other thing is we're going to look at some of the annotations you can do, and there's an enormous number of annotations, and we're just going to look at a few of them, and I'm going to encourage you to look at more of them in the afternoon period. So so I broke a recipe that was well, this is kind of based on a recipe that was in the YT docs in the cookbook. I broke it up into different Jupyter cells to try to explain the different steps that are going on there, and hopefully that helps it be a little bit more understandable. So slice plot can take a sequence of fields, so any sort of sequence in Python, a list or a tuple, and it'll generate slices for all those fields, and then you can access those different fields using the same sort of dictionary-like behavior that Madikin had demonstrated in the regions thing, where she was selecting just the density part of a region. We're going to use some features of matplotlib to control the layout. So YT is going to do the cutting of the data, figuring out what data to display, and the scaling of the data, and basically generating everything. But then we're going to rely on matplotlib to actually do the layout. And this is a common thing that we might want to do. Using matplotlib gives us a lot more ability to fine-tune the structure of our plot. So I'm going to load matplotlib in the standard way, loading it as pyplot as plot. And I'm going to load from the Axes Grid toolkit the image grid. And an image grid basically allows you to create an array of axes. And that's the first thing I'm going to do, is I'm going to create a figure. So plot.figure just returns a matplotlib figure object. And that figure object is where I want all of my data to reside. And then I'm going to create an image grid. And the image grid takes the figure that it's going to live on. It takes, this is just the location in the figure in terms of the normal coordinates in a figure that the plots are going to sit within. And so this is kind of like the default, a little bit, give a little bit of a margin on all sides. Then it takes the number of rows and number of columns, 2 rows, 2 columns. Think of this as an array. Some padding between it. I don't actually know what this 1.0 means physically. It's one of those things that you play with. If there's too much padding, you make it smaller. If there's too little, you make it a little bit bigger. Sometimes these things require a little bit of iteration. Label mode L means that I only want to show the labels on the left side and on the bottom side of my grid. Since I have an array of axes, I don't need to show the label everywhere, and I'll point that out when we make it. Each axis is going to have a color bar, and I put a little padding between the color bar and the axes just because I like the white space there.
Hey, Mike, I have a quick question for
Yes.
you. Based on the previous slice that you showed with the zoom, can you tell us whether YT scales the color map when you zoom like that, or whether it sets the bounds to the data set min and max?
Oh, so my understanding is it is setting it to the local slice.
Okay. Yeah.
So, I mean, look at this. This is a much smaller data range than when I plotted the full thing, right?
Right. Yeah. Yeah.
So it seemed I mean, it seems to me that it's dynamically adapting. Whether there's some padding to it, I don't know, but it is looking at the local region when it's setting the bounds.
Yep. Okay.
You can, of course, override that,
Mm-hmm.
right, with the set zlim that we looked at before. This is just one of those fun bits that, because I divided this up into different cells, the Jupyter is interpreting the output of the previous things and actually showing me something. So this is what my bare image grid looks like. You can sort of see the L here. I only have the tick marks on the left and on the bottom, not here, because this axis shares the same X as this one and the same Y as this one. Anyway, that'll go away in a second. Now I'm going to produce a list of fields: density, velocity X, velocity Y, velocity magnitude. For most codes, velocity magnitude will be computed on the fly because it's just the magnitude of velocity X and velocity Y. We have a code where, of course, that's not the case because we like to cause trouble for YT. But for most codes, this will do the right thing. I'm going to make my slice plot. I changed my notation. I'm just calling it P now. And I'm going to, in there, by default, it sets the log for everything. I'm going to turn off the log for the X velocity and the Y velocity. They can have negative values, and I don't want that. So I'm going to disable that. And this is not going to do much. It's going to say, I'll talk about this bit in a second. Oh, actually, it does do much. Hang on a second. It's going to say that it's done, it's looked at each of those. So density, velocity X, velocity Y, velocity magnitude. So it's actually looked at the data, produced the slices for those, gave me a little warning that there's some negatives here. And if you're doing a log, it's going to switch to symlog later. And then here's what it outputs. It actually outputs, when you're sitting in Jupyter, it shows what those plots look like. So here I have 4 plots. They look quite nice. I'm not sure what's going on with this one, but I didn't make that data set. But we want to arrange them in a nice grid. So we have the plots. They're there. They're sitting somewhere in the internals of YT, but currently they're 4 separate plots. I want to make a nice tiled grid. So what I need to do now is I need to reach into that plot object, access the underlying, that slice plot object, access the underlying plot data, and link it to those matplotlib axes that I've just created. And so that's what we're going to do now. And this is something that's not obvious, I would say, because it requires some knowledge of how YT puts things together under the hood. That's why the cookbook is such an invaluable resource, because this information is provided there. So we're going to use that matplotlib layout. We're going to loop over the 4 fields that we use to make our plot, and we're going to assign the underlying plot itself to one of the axes on that we created with that image grid. There's some quirk in Jupyter that I didn't have time to debug when I wrote this, that if I don't sort of manipulate the slice plot object right now, this all sort of falls apart. That's only because I decided to split this code up across a whole bunch of different cells to make things better. So if I figure out a fix for that, I'll fix it. But I have this zoom in here just to sort of refresh the plots. Then I loop over my fields. This is the list of fields I input. For each field, I access the underlying plot. So the slice plot object has a plots. It's not a dictionary, but it's something that is like a dictionary that holds the actual plot. So this is my current plot. I set the figure attribute of the current plot to be the figure that I created. That's the overall matplotlib figure. I set the axes to one of the 4 axes that I created. So I use the enumerate here, so it'll be 0 the first time, 1 the next, 2, and then 3. And likewise, I set the color bar axis, that's what CAX is, to the corresponding color bar axis that the image grid created. And then I need to tell the slice plot to sort of redraw things, and that's what this last command does. And I do that. I don't see anything because now these things live in that matplotlib figure. If I look at the matplotlib figure, I get this nice plot with the 4 separate fields all shown on the same figure in that 2x2 arrangement that I had asked for. This is now being controlled by matplotlib. At least that's the way I think about it. This figure is a matplotlib figure. And so I can use the matplotlib commands to operate on it. So for instance, if I want to save it, I can use savefig, which is the matplotlib command. And let's see if I saw that terminal open. And I already forgot what I called it. I think it's multiplot. And if I could type correctly, here's my underlying plot. And it looks small. You can matplotlib allows you to set the DPI and so forth, so you could play around with it and make it the resolution that you want it to be. But that's a nice way to be able to produce something. So this is sort of there's 2 ways you can think about using, or 2 ways I think about using YT. A lot of times you have a notebook that you just run through when you're doing the analysis, but then you make the pretty sort of publication quality plots when you're writing all this up for paper. And so putting everything together on a common set of axes is something that you might want to do in that case. There's more advanced ways, really cool looking things, if you look at the notebook, that really rely on using matplotlib to control all aspects of the layout. So for instance, producing some sort of plot that looks like this, that's pretty nifty. Don't ask me what it is. And so I gave a link to one of the cookbook recipes that shows how to do that. And now I'm back to my notebook. As I mentioned, there's a lot of ways to do annotation. In in YT, these are generally all termed callbacks. And so the idea is once you make a slice plot, or as we'll see tomorrow, this also works for projection plots, you can add a number of callbacks to it. These are, this is basically a list of the different types of annotations you want to do. And when you make your plot, it's going to run through all those callbacks and add all those annotations to the plot. So I'm going to remake my plot.
Can I ask a question first?
Yeah.
Mike? So if you go back to your 4 panel, maybe.
Yeah.
Okay. So when I'm making my figures, these numbers are all right on the money for me because I run Galaxy stuff.
Yeah.
But I don't actually want that times 10 to the 7 at the top of my color bar. What I really want is this to say velocity y, and then the units to be 10 to the 7 centimeters per second.
Right.
Do you know how to do that? I don't know how to do that. I don't know. Maybe I've done it before, but I can't remember.
If you're asking me, can I do it for you right now? The answer is no.
Okay. I'm sure it can be done.
It can be done.
Yeah.
I personally like that 10 to the 7, but that's maybe a me thing.
Yeah, I guess it all depends on how close you're going to want to squish your panels too.
Right. So basically there's definitely a way to do it. In the most extreme absurd way that you could do it is create a derived field where you just divide
Right.
it.
Yeah. Yeah.
I'm
that
sure
might
there's a
actually
way to
be what
do
I've
it.
done.
I'm sure there's a way to do it other than that, and maybe Matt or Madi can.
You can set the units to be 10 to the 7 centimeters per second.
Okay. So somewhere.
Awesome.
So under set_unit. So yeah, if you call p.setUnit density, or I'm sorry, velocity y. Yeah, set_unit. And you can specify more than one at a time here in the call. You can put it in a list. So velocity x, velocity y. And if you set it the second argument to 1 E7 times, I'm sorry, in a string times CM over S, it should do it.
Let's find out, Matt.
Yeah.
Oh, look at that! Indeed.
Very cool. All right, cool. Thanks.
Although it only did it for velocity x.
Oh, well, maybe you got to call it twice then.
Or
Sorry.
maybe I spelled velocity wrong.
It's
Nope.
possible.
No. Okay, so I guess you got to do it twice.
Yeah.
Okay,
Very
cool.
cool.
You can also access all of these like with the matplotlib axes that you assign them to, and so you could manually override.
Yeah,
whatever
that is messy.
That is very messy, but it is an option if you really feel like getting into the nitty gritty of matplotlib.
And
Cool.
I try to avoid that as much as possible.
Yes, it's a good
Axes
thing.
in particular in matplotlib are
Yeah, they can definitely, but because YT is like all the viz is subclasses of matplotlib objects.
Yeah.
You can access the axes through the plot interface that you are creating all your plots through. And so
you can pass the keyword arguments directly through.
Yes,
Yeah.
right. And so that's another option that you could take, but it's not as sophisticated as overriding the units, but it is another option.
And I won't ask Matt how to get rid of that 1.0 there. But,
I would not be able to tell you.
Okay. Well, thank you for the questions, and most thank you for the help. That's cool. So let's see. I have a little bit more time, so I'm going to show the velocity field. This is something I always like to plot. There's actually several different ways to visualize vectors in YT. Annotate velocity relies on the code knowing your front end knowing what the velocities are, which is set up, I believe, for pretty much all the main simulation codes, and it'll show via little velocity vectors what the actual direction and magnitude of the velocity field is. And the factor here is basically a way for you to thin out the velocity field. I think it's in terms of number of pixels. So you can see I can really show lots of arrows, maybe lose some of the detail or thin it out some and get a sort of coarser feel for it. There's ways to normalize the velocity arrows or provide a scale to them, which I leave as an exercise later on to look at the normalize and scale. So these arrows sort of overlapping perhaps is a bit confusing as you look towards the center, but there's ways to reduce that. There's also streamlines. So there's an annotate streamlines. Streamlines are basically where you integrate you pick some starting point and you integrate the trajectory of say a fluid element by using the local velocity field to make it to tell you how the velocity is changing. And so you get these nice long streaks in your plot. And there's also a line integral convolution, which to me is basically what happens if you ask Van Gogh to visualize your stuff. It kind of looks nice and streaky like that. Visualizing the grid is something I always like to do as well. Again, there's a callback for that called annotate grids. And if I do that in my slice, it'll actually show the patch structure of the AMR. You can see the different levels. They're colored in different colors. Some of the colors don't show up too well here, so there's kind of a purplish color hanging out here. But you can see the nice, this is a nice way for you to, for instance, look at the domain decomposition in your simulation, or to make sure that the resolution's sitting where you want it to. You can also visualize not just the patches that make up your grid hierarchy, but you can look at the individual cells. If you turn that on for this, it'll look crazy busy. So you only want to do that when you're really, really zoomed in. That's not something I use much, but annotate grids I think is a nice way to just to get a feel for what your simulation code is doing. And so there's a lot more. You can draw spheres, you can draw contours. I already mentioned streamlines, and I encourage you to look at some of these after this afternoon to add annotations to your plots. I didn't do it here, but I'll do it in the projections tomorrow. But you can also do the slice plot on a region, like Medikin showed us this morning, where you can cut a sphere and then just look at the slice in that sphere. And so we'll do some of that with projections tomorrow. We'll look at visualization, these visualizations with regions. We'll also look at off-axis stuff tomorrow. So when your slice plane is not aligned with X, Y, or Z, we'll do it for projections, but it's the same basic idea. And a final note, there's a simple wrap, this should be simple wrapper called Plot2D, which allows you to plot 2D data. Where is it? Oh, so this is just what the call is. Allows you to plot 2D data, which essentially a slice is a 2D visualization of your 3D data set. If you have a 2D data set, it's kind of trivial, so you don't have to pass the orthogonal direction. That's basically the main thing that this happens. One caveat, you can still use the main slice plot for your visualization, even if your 3D, the orthogonal direction is going to be for your 2D data set is going to be the direction that you're not simulating, most typically Z. If you're 2D, you just have X and Y in your code. One thing, however, is for 2D axisymmetric data, that's something we do a lot. Then you're modeling R and Z, and you're going to pass theta as your orthogonal coordinate. But this is something that the Plot2D should do naturally. So that's all I had on slices. And as I said, tomorrow will sort of be the part 2 of this, where we dig a little bit deeper and do things on projections and look at some of the same stylings that you can do there and some more advanced stuff. So I'm going to stop my share so I can actually see people. So we got any more questions? No.
Did you link to all of the annotations that are available in your annotation docs in your?
I'll do it in the next one.
Okay. Okay, great. Yeah, because I encourage all of you to look at the annotations that are available. You can like annotate with like labels, like you could label specific points on your plot or something like that. It's not just like field-wide annotations. So there's lots of really nice customization that you can do.
So and I'll show this one tomorrow, but one of the things I do often is I want to show the simulation time on my plot.
Yeah.
So there's an annotation for that. Yeah. I was going to show more of those tomorrow.
Okay. Okay. Perfect.
The multi-panel figure is the most conceptually challenging thing that I showed, but I think that's such a common thing you want to do. So I wanted to go over that.
Yeah, I think that's something that's super important. All of us do it at some point, I think. So
in fact, writing this inspired me to maybe explore whether there could be some more higher level function to do all that magic.
Ooh, more YT contribution.
I think there should be.
Yeah.
I think there could be. Yeah.
I support it. I think that'd be great.